Sagittarius. Going live now. 3, 2, and 1. All right. Set.
Great.
Thank you.
Well, thank you for inviting me. And my name is Matthew Shetrone. I'm the Deputy Director for University of California Observatories. And so that's our logo up there on the screen. And you can see that we're not just University of California, Santa Cruz. We're all of the University of California campuses, plus Livermore but I've only been in the job for 2 years. So I joined just before the pandemic struck. So I got up to Lick Observatory after many years and was able to look around, and then I haven't been back since. So I'm really looking forward to seeing our other observatories out at Keck in person rather than observing remotely. But what I'm going to talk about today is some research that I've been doing over the last 10 years or 15 years before I joined UCO. And it uses observatories in space, on the ground. It's international collaboration. So whenever I talk about another observatory, I'm going to try to give a little bit of background where that is. And I'm hoping to give you a feel for how we use some of that data and combine it to look at big picture results. So let's see. Okay. So I consider myself a galactic archaeologist, which, you know, sort of has got a great title, but nobody really knows what that means. So what it really means is you imagine an archaeologist, they're off looking at the history of things. And that's what I do, is I study the history of our local neighborhood or the Milky Way and try to understand how it got to be where it is. So right now, what you can do is say, you can go out and look at an object. So I have a picture of an object there. And you say, okay, from basic astronomy, you can ask questions like how far away it is and how it's moving through space and what's it made out of. And then the archaeologist part is, how did this thing come to exist? And how do we, studying it, understand our place in the universe a little bit better? So that's sort of the goals of archaeology. And so that's what I'm trying to apply here, is looking into the past to try to understand how things, how we are situated in the universe now. So the types of things that I need are distances and ages, and then I need how things are moving, their space velocities and their radial velocities. And I need to know the chemistry of things. And so, and if you can imagine you're doing archaeology, you don't necessarily just want to go and dig in one small location. You need to kind of cover a larger area to understand the context of the things that you're finding. So it doesn't help to go and dig down in one little square and say, oh, look, I found a pot. And they're like, well, is that a cook pot, or is that in a midden, or, you know, how is that in context to the culture that it was sitting in? So you kind of need to understand the bigger picture. And so for me, the bigger picture is studying more than just the most nearby stars. It's really studying as much of the Milky Way as you can get, but because there's so many stars, that becomes difficult. So as kind of background, I'm going to show you a simulation now of a galaxy being formed. And the galaxy sort of ends up looking a bit like the Milky Way. And so it has kind of a history that is similar to the Milky Way's history. So, but it is not necessarily just of the Milky Way. So there's this number Z up here, which is a redshift. And I've given you kind of a scale over here when we hit Z of 3 and then 1. And so I will kind of narrate as we go through. So not much happens here at the beginning. And then boom, we have stars forming and little clusters or groups or baby galaxies. And then they start falling in together and forming. So here we're at Z of 3. So 11 gigayears ago. So that's before the disk forms. Eventually, this simulation is going to show a face-on Milky Way-like galaxy, but it doesn't look like anything like the Milky Way yet. So you can sort of see things are still falling in, and maybe they're in big, wide orbits. So we're approaching Z of 1, which is 7.8 gigayears. So that's even before the sun has formed. You can see there's a lot of activity going on, but still it barely looks like a spiral galaxy face on. You can see dust lanes being ejected, being moved around, lots of activity. Not the kind of place you necessarily want to have your, civilization growing up in. All right, we're at 0.5 Z, so that's 5 gigayears, 5 billion years. So that's the age of the sun. So now it's starting to look a bit more like a normal spiral galaxy. And you can sort of see some spiral arms forming. And so the size here is, the box is edge to edge 50 kiloparsecs. And just for context, we are 8 kiloparsecs from the center. So we're sort of about here in this whole big mishmash. And you can sort of see things are still falling in this particular simulation. Again, that's not exactly what the it's not intended to be what the Milky Way is, but give you a feel for it. Here's a different view, and this one's edge on. Just so you can sort of understand a different perspective on that. So again, you have the beginning. So we're at the age now of Z of 3, 11 gig years. So that's when globular clusters are forming and forming in the halo. And so now you can understand why they would be in the halo, because there's no disk to speak of. There's nothing disk-like yet. So anything that forms is going to be in the halo, kind of by definition. Okay, we're getting close to Z of 1. Now we're starting to see a little bit like a disk forming, sort of a flatter area here, but it's not particularly flat. This is going to eventually be edge on. That does not look edge on. All right, approaching Z of 0.5, which is 5 gigayears. That's about when the sun would have formed. So suddenly, boom, we start to see a disk, and the sun would have formed. So it's not very long after the galaxy starts to look like a spiral galaxy that our sun formed. So it's sort of an interesting take to look at these simulations, assuming they're correct, and sort of think about what it was like right when our sun was forming. Things were just getting together, just getting organized as far as a galaxy is concerned. Okay, so it's pretty calm at this point, and things are not falling in and disrupting our galaxy. If they did disrupt that galaxy, it could easily change from a spiral galaxy to an elliptical, going back to having no structure like this and only that kind of mishmash of things moving around. All right, so that's the context. So I want to dive into talking about the halo, since that's the first thing that formed. And to study the halo, in those simulations, you saw things falling in, moving around. And so that's where we see streams of stars as they fall into the Milky Way. They get disrupted and they form, streams. So here we have a long stream. This is an image from Sloan taken of a large part of the sky, and sort of just density maps. And so you can sort of see the Sagittarius stream here. And there are lots of little other streams here. This one actually belongs to a globular cluster. There's another one here called Triangulum. So people have made a lot of work to identify all those streams in our galaxy. And it's sort of a big success that those models showed those streams. And now we're seeing them in detail. So here's a different kind of simulation. Here's the Sagittarius galaxy. which fell into our galaxy kind of late. Here's where the sun would be. Here's our spiral. This is just kind of a simulation. And here's the core of the galaxy, and it's moving along like this. And you can sort of see there's a leading tail, a tidal tail that gets ripped off by the tides of our galaxy. And then there's a trailing tide. And if I push play here, you can sort of see that while it looks like they're kind of in a haphazard fashion, you'll see that they're actually on a plane. And so you can sort of imagine now, okay, this thing is falling in and it's making these loops, but it's really doing that on the sky. Okay. All right. So to study the chemistry, to get the chemistry parts of this, I'm going to turn to a project that I've been involved with for about 15 years, which is it's called Apogee. And it's an infrared spectroscopic survey that has multiple fibers plugged into a plate. And then they take that plate, put it on the sky, and we've set each of those plates up designed for a star or different stars, about 300 stars. And some of them we go back and visit many times so that we can get deep images. And so this is just some characteristics of it. It's in the H band, if you know the infrared, but it's at 1.51 microns to 1.69 microns. But it is sort of the leading spectroscopic survey. There are some that are better, but there are very few that are of the quality that seems to get produced by Apogee. So here's what some of the spectra look like. So everybody knows OB, A Fine Girl, Kiss Me, sort of the sequence of stars. And this is what those stars look like in the H band for Apogee. There's little gaps here. This is one detector, and then it's abutted by another detector, and then abutted by another detector. That's why there's a little gap here. There's some telluric from our atmosphere features here, and so that's why it kind of looks kind of crummy right there. But you can sort of see M stars are very cool in temperature, and they have lots of molecules, so they have very deep lines. And these O and B stars are very hot, and so they have very few lines and only hydrogen lines. So these are big hydrogen lines. So how do we turn these spectra into abundances? Well, we have to use a model. And here's an observed spectrum from a globular cluster at the top. And then here's the model that we came up with to match it. And what we do is we have in the model, we have different molecules and elements and what they and their strengths. And so we just kind of go through and match the observed with a synthesized one. So you can sort of see this big strong feature here. This is from aluminum. It's the black one here. And then this sort of magenta colored one, that's a silicon line. And so you sort of trace it up. There's it is in the synthesis, the model. And then here it is up here at the top in the observed. So you can sort of go through and say, oh, here's this molecule radical OH. And you can sort of see, okay. And so this is where we can get the oxygen abundance. And then these little band heads here for molecules are from CO. So once we know O, we have the strength of the CO, so then we can get C. Unfortunately, there's also cyanogen, CN. And this is where we normally would get nitrogen, but you can sort of see in this star that these features are really weak, and so we can't get nitrogen very easily for this star. But iron and other elements. So this is sort of what we do to get the abundance is we create a model, temperature of the star, the surface gravity, and the strength of all of the features. Okay, so This is a kind of a simulated picture of what the Milky Way might look like. This is kind of where we are in the galaxy. And then this is what Apogee does, is it puts a plate on the sky and observes all the stars in there, but they're not all at the same distance. So you get this funny sampling, kind of little pencil beams across the galaxy. So let me back up one. So here's the center of the galaxy. We're out here, and you can sort of see those pencil beams radiating out. Because it's in the infrared, we can actually look through a lot of the dust. And so we can actually get past the center of our galaxy. But even, you know, there is so much dust there, it sort of stops us from getting way out here, but we can get past the center just a little bit. So this is sort of what the sample looks like. It's not everywhere, but it's sort of our best guess or our best estimates on trying to make even sampling across the Milky Way. You can sort of notice we missed a whole quadrant here, and that's because the first Apogee instrument was in New Mexico at Apogee Point Observatory, and it can't reach the southern hemisphere, so there's all the southern sky that we can't actually see. We can see some of the southern sky, like the center of the Milky Way is in Sagittarius, and so it's south. But in later years, we've actually built a clone of it at Las Campanas in Chile so that we could fill in this area to sort of make a more complete map of the Milky Way. This is a different view. So it's kind of from the side of the Milky Way, and you can sort of see this is what it looks like. There's some funny projection effects because of distance. Were actually pointed out along the Milky Way, and it looks like these things are curved, but they're not really curved. They're just straight pencil beams, but there's sort of a funny projection there. But you can sort of see there aren't very many stars up here. So most of our effort is in the disk of the Milky Way, with a few up here, because we want to sample the halo, and we want to sample the bulge, and we want to sample the disk. So, and we're combining that data with a new satellite, Gaia, and Gaia does proper motions. So it sort of studies the whole sky and looks at very distant quasars and galaxies as not moving, and then everything else moves. And so it can get the position and the motion of all the stars in the sky. And this sort of gives you an idea of what it reaches very well for getting distances, but it can go much further if you're looking at motion instead of distances. So this is how far it can reach to get motions of stars on the plane of the sky, projected. So you can see it can get into the middle, except for the fact that it works in the optical, and so it has difficulty getting into where all these dust bands are. Okay, so again, just to remind you, the Sagittarius stream is one of the things that we're studying in the halo to sort of understand what does it look like? What does this galaxy that has fallen in called the Sagittarius galaxy, what does it look like? You know, is it different? And are the leading tails different than the trailing tails? What about the core of the galaxy down in here? Is it a little bit different? So Apogee goes and puts a plate and goes and studies a pencil beam here and a pencil beam there and a pencil beam in a couple other locations, and then we compare. So this is what the Gaia satellite shows for the motion of these stars, and this is in velocity versus angular momentum or energy. And you can sort of see most of the galaxy kind of goes around in a disk, and it has very little angular momentum off of the plane of the disk. It's all of its angular momentum is confined to the disk, and then Sagittarius has this very distinctive kind of plane out here, and so it's easy to identify the stars that belong to the Sagittarius stream. And so if we then go and take those stars and say, okay, how do their chemistries compare? So here's the Sagittarius core of the stars. Most of those seem to be, this scale here, this is iron compared to hydrogen, where 0 is exactly like the sun. And it's on a log scale, so -1 will be 10 times fewer atoms of iron compared to hydrogen than in the sun, and then 100 times, so it's a log scale. And so most of the ones in the core are a little bit more metal poor, not 10 times, but more like 3 or 5 times more metal poor than in the sun. But they look different than the ones that are in the trailing arm and the leading arm. So the trailing arm has a big spike here that's not quite as metal rich as the core. And the trailing arm. And then the leading arm looks a little bit different also. So each of the parts of that galaxy looks a little bit different as it's being torn apart. So we have to kind of use our imagination to say, okay, so what's really going on here? So you have this galaxy, and it's evolving too, and it's making stars, or has been making stars, and then it's kind of falling along. It's kind of falling into our galaxy, and it's starting to get ripped apart. And so what parts get ripped apart first? Well, maybe it's the outer parts that get ripped apart first. And the outer parts are the oldest parts. And the oldest parts are the ones that are most like the Big Bang chemistry. So they don't have a lot of iron. They're very metal poor. So we're seeing the stuff that gets ripped off in the arms is more metal poor than the core of the galaxy. So we're starting to understand, okay, this is why the halo of our galaxy is made up of lots of metal poor stars, because as things fall in, the metal poor stars get pulled apart and distributed into the halo of our galaxy. So, we have some conclusions that we could draw about the halo, and it seems like those simulations at the beginning sort of make sense now. You know, you've got lots of things falling in, getting stripped apart, and then they leave little balls of stuff behind. You know, the most concentrated bits of stars are the last things to get shredded. And those parts tend to be more metal rich. And their chemistry actually looks unique. I didn't go into that part, but if you go in and start looking at more than just iron, but aluminium, you look at elements like cerium and magnesium, those elements in ratios with iron start to look unique also. So we can use those ratios of elements to sort of start to tell what belongs to what. And that's part of the archaeology, is understanding, oh, these two things belong together and this is something different. So let's go in and talk about the disk of the Milky Way. So for a long time, people have talked about gradients in the Milky Way. And the gradients that they're looking at are in iron. Again, 0 is what is like the sun, and this is radius from the center of our galaxy. And so people have known for a long time that there's sort of this trend that moves out that says, okay, it's sort of a little bit more metal rich or enhanced compared to our sun, and then it declines as you go to the outer parts of the disk, and then it flattens out again. But now with these big surveys, we can actually start to probe more than just the general trends. We can go in and look at the details of what the distribution is, because you can sort of see, yeah, that's a good trend, but look at all the stars that are way out here and way down here. You know, those deserve attention. You know, why are we only looking at the ones that are in the the where most of the stars are. What's up? What's the story that these stars could tell us, or these stars? Do they have an interesting story, and is it relevant for understanding something more important about our Milky Way? So that's what I want to go to talk about. So there's, how do you take this distribution and figure out ways to describe it in such a way that is useful? So one of the ways is you go to somebody who's really good in mathematics and say, okay, how do we describe this? And an astronomer would say, put a Gaussian on it, put a Gaussian on it. Well, it doesn't fit well with a Gaussian because there's skewness. And so here is example of what a skewness. Gaussian should be a nice shape like this, but there's this wing, this long wing out on this side. And so each of these are in groups of radius. So the black here is the part that's closest to the center of our galaxy. So that's this black curve here, and it's metal rich on average. But look, there's all these metal poor stars that are in there as well. And then here's our the sun is at about 8 kiloparsecs. So it's sort of this teal colored here. And well, sure enough, 0 is where the sun should be. So it makes sense that we're kind of there. And it's sort of Gaussian shaped, more or less. But then as you go to the outer galaxy, you have the opposite, where the skew actually goes the opposite direction. The tail points in the other direction. So that's one way that we can describe this, is with this skewness. So how do you make that kind of a distribution? So what do astronomers do? You have to go to a model, and you try a bunch of different models, and you hope that some of the models fail, because if they all describe the process, you haven't learned anything. So here are two different models. One is where you have these stars forming at some metallicity, and then they, over time, their velocities just sort of drift out. They have their orbits. Some of them are a little bit elliptical in one direction, a little bit elliptical in another. And so they kind of, at the early times, they're very tight in our model. And over time, they kind of spread out a little bit. And sure enough, you get just a tiny amount of skewing from the metal rich in the center part of the galaxy here. It kind of skews out this direction, and then the outer part of the galaxy, which is metal poor, skews a little bit the other way, but not very much. So here's a different model where we don't have the orbits just sort of evolve with their natural ellipticity, where the stars actually move from where they're born. So this is diffusion or migration. And so the stars actually move from the orbits they're born in, either in towards the galaxy or out towards the galaxy. And you can imagine how this would happen. You have this giant molecular heavy cloud that's sort of like the Orion star forming region. And then you've got some star that's kind of cruising along in kind of a slightly faster orbit, and it comes across this thing and it gets a slingshot effect. As it passes this giant molecular cloud, it gets torqued a little bit as it passes it. And so its orbit changes. This is just like trying to get out to the outer solar system. You get slingshots. Our spacecrafts get slingshots from passing the Earth, passing Jupiter, all these planets that it passes. It uses that to change its orbit. This is the same sort of thing. So it gets a little bit of a slingshot, and then its orbit changes, and sure enough, you can get this skewness. So this idea is only about 10 years old, and this is really the first good proof that this migration, this stellar migration, might actually be happening. And so we're happy that this model failed, and this model still might be wrong, but at least it matches a little bit better. And so how much do the stars migrate? Well, in this model, in order to match the data a little bit, it looks like the stars have to migrate about 5 kiloparsecs over their lifetime. So over 5 billion years or so, they need to move about 5 kiloparsecs. Remember, the sun is at about 8 kiloparsecs. So that's a long way. That means that you look at around us and you see stars, and you might wonder, okay, these are our neighbors now, but they weren't necessarily our neighbors a billion years ago, or when the sun was formed. All right, so there is another satellite called Kepler, which was really designed to look for planets going around stars. By staring at the same patch of the sky for a long time, it could look for eclipses as a planet would go in front of a star. But, you know, planets, who cares about planets? So, you know, most people care about planets. But stellar spectroscopists found that, well, all of this other stuff, when there weren't planets involved, there was a tremendous amount of information that we could learn about the stars themselves, because it's staring at these stars that are not changing. But then you go into the details and you can see, oh, wait, they are changing. They're pulsing ever so slightly. And that pulsing, if we match its frequency, we can learn about their mass. And so we've started to learn that what the masses of some of those stars are. And then we look at their chemistry, and we've discovered that the carbon and nitrogen abundances are related to the mass and the age of those stars. So taking a ratio of the carbon and nitrogen ends up being kind of a proxy of mass or age if you're on the giant branch. So it doesn't work great for the sun because the sun's not a red giant. But as the stars go up the giant branch, they have these big convective envelopes, which changes the carbon into nitrogen, or dredges up where carbon is being turned into nitrogen in a nuclear process in the star that gets brought to the surface. And so we're actually seeing the nuclear fuel brought to the surface. So we've been able to use that as a proxy for age. So here's a ratio of carbon to nitrogen, and 0 here means it's sort of the same ratio as the sun. You notice none of these, hardly any of these, have the same ratio as the sun, which is okay, because as I said, as these stars become red giants, they start showing the process of the fuel being that they burned up over their lifetime. So the oldest stars have a different carbon to nitrogen ratio, that's these up here, to the youngest stars, which are sort of the bluish colored ones. And there's a lot of scatter in there, but to first order, you can sort of separate young and old. And maybe you can't say for that star right there, is that a young star or is that an old star? You know, they sort of get into a gray area, but as a population, you can sort of make that distinction. So earlier I had said that there is this gradient that we know about that says as you move out in the radius from the center of our galaxy, the trend was you get more metal poor. So, but if you look at young stars and old stars, you get a different trend. So when we first saw this, we were a little bit baffled until we remembered that other study that looked at migration. So, and the way migration works is that you might move 5 kiloparsecs, sort of from here to here, over your entire lifetime. So if you can imagine a star is young, it doesn't have time to migrate. It might migrate just that far because it's very young. It hasn't had time to do it. But given time, it might be able to move from up here over to here. And so what that does is it flattens out this curve. And so you can sort of imagine that this is just washing out this trend with smearing it out. So that's sort of another piece of evidence that this idea of migration might actually be true. So if we instead look at this in a slightly different way and look at this as a cut, instead of looking at it as a cut in a vertical direction, we're going to look at it as a cut in the horizontal direction. So we're going to say, let's just look at some metal-rich stars, sort of this bin here, in the old stars and the young stars. And so here's this indicator, and I've said, okay, this on this side of the indicator, you're old, and on this side, you're young. And this is just in one small group of metal stars. And you sort of see, okay, if you're young, you're probably going to be in this metallicity range. You're going to be in the inner part of the galaxy, 5 to 7 kiloparsecs. So the sun is at 8 kiloparsecs. So this is inside the solar circle around the Milky Way. And then if you go to the older stars, they're going to be in the outer part of the Milky Way. So the stars have moved from one part of the Milky Way to another part of the Milky Way. So we have some new information based on some data and some models that have a suggestion about how things evolve in the Milky Way. That not only do we have that early Milky Way where you've got stuff falling in, and then eventually about when the age of the sun occurs, things settle down and it looked like a nice normal spiral galaxy, but apparently things are still very chaotic, that you still got stars that are going around the Milky Way, but in the same time, they're also slowly kind of working their way outward or inward along there. So it sort of begs the question, where was the sun born? So let's go back to this plot. The sun has a ratio of 0 here, iron to hydrogen, because that's the way this is sort of defined. And so if you looked at young stars, stars that are only a few million years old, they fall on average. There are some here that are inside and some outside, but the bulk of the population is sort of at 8 kiloparsecs, which happens to be where the sun is. So that seems great. I mean, you sort of look out at the Pleiades, and if we take a spectrum of a Pleiades star, it has sort of the same composition as the sun, but the Pleiades just formed. So isn't there some sort of evolution of chemistry over time? Why is the old sun 5 billion years ago not like the, or why isn't there an evolution so that it's more metal rich than it was when the sun formed? Well, one explanation for that may be that the sun has moved. So maybe the sun, these are young stars. So over time, this entire line might move up a little bit with chemical evolution. So maybe 5 billion years ago, this whole line moves down a little bit, and it may be down here where bulk of the population. And then the sun migrated from this location out this direction. So that's the hint that we have, and we're trying to figure out ways that we can get more evidence to support that hypothesis, that the sun wasn't born in the location that we're in now. That's a tricky thing to solve, but that's one of the things that is one of the remaining mysteries, is where was the sun? Was it born way out here in the boondocks? We talk about us being sort of out in the boondocks of the Milky Way, but maybe that's not where we were born. We were born in the inner city, and we moved to the suburbs over time, which would be a really different kind of story to tell for our solar system. Okay, so that's sort of what galactic archaeology is all about. That's the kind of questions that we're trying to ask is, where did we come from by looking at some of these giant data sets? So let's go back to that image from the start. We had this image of things, and traditional astronomy is a bit more like stamp collecting and cataloging, where that's the first steps in classical astronomy, is to catalog things. And then eventually you need to figure out, okay, we've got all these catalogs. Now let's see if we can put models to them and figure out some hypotheses and then figure out ways to test them so that we can sort of run the picture backwards in time and say, what was this thing that formed into this looking structure? What did it look like before? And so this is actually what that object is. So it's some sort of, moon. All right. So I'd be happy to take some questions. If you have any questions. Oh, I see a lot.
Yeah, we do have a lot of questions, and Dave seems to be the winner so far. So I'll start from the top. The first question he has is, the simulation you showed by Philip Hopkins took just a few billion years, less than the age of the universe, to form a spiral galaxy. So how is it possible for the Hubble Deep Field image to show spiral galaxies from a few billion years after the Big Bang?
Right. So that is a great question. So when we look at some of those spirals, if we go back to that simulation, well, maybe I should go back to that simulation. Let's see if I can. There we go. Oops. Did it stop sharing?
I don't see it.
Okay, so let's try again. All right.
Yeah.
So if we go back to one of these simulations, so most of where we're looking at the Hubble Deep Field, those are very, very old star images. Let's use this one. Mm-hmm. And so we don't really see spiral galaxies older than about Z of 3. So you need to have things that are Z of 2, redshift of 2, 10 billion years. So let's wait till we get to 2, and I'll see if I can pause it. And then you can decide whether that looks like a spiral galaxy or not. And if it doesn't, then maybe you say, well, maybe this simulation isn't so great. Mm-hmm. So, it didn't pause. It took us back to the beginning. Okay. So the point being, or maybe I pause it and then do this. Yes. 2, redshift 2. So most galaxies in the Hubble Deep Field don't look like nice, pretty spirals if they're very, very distant. Some of them aren't so distant. And so those would be ones that look like this. But, you sort of think and say, okay, these are snapshots. So a lot of the Hubble Deep Field galaxies look like irregulars or ellipticals. And that's because they're just forming and stuff is falling in. So you can tune this particular simulation by changing dark energy, changing dark matter properties until you get it to match what the universe produces. So that's why lots of people want to go out and look at these distant fields and not only take images like the Hubble Deep Field, but then they need to know what's the redshift, what's this Z number for every one of those galaxies, so that you can put it in context about its age in gigayears.
Let's see. And then Dave has another question. Actually, he posted 2 questions, but they're kind of related. So one question he had was about the distance from the sun. You mentioned it's 8 kiloparsec. Mm-hmm. So how is that determined? And also, and how do astronomers know where our sun is in the Milky Way?
Right. So that is tricky. You need some way to know you're here. And one way we can do that is we can take images of stars that are, we now can take images of stars in the center of our galaxy with things like the Keck telescope in the infrared, because the infrared cuts through all of that dust.
Mm.
And we've found, Andrea Ghez has found that giant black hole at the center, and there are stars going around that black hole. And so if you take those stars and say, what are the colors of the star? How bright are they? Are they giants or dwarfs? And if they're giants, let's match them up to giants that we have models for.
Mm-hmm.
And then we know how bright they are in the infrared, and we know how bright those stars are nearby. We use that distance scale kind of thing to determine what the distances are.
Mm-hmm.
That's what we can do now. Before we had infrared instruments, we had to do all sorts of fancy things to triangulate our way to the Milky Way center by looking at velocity speeds and giant molecular clouds and radio observations to infer our distance. And there was always some question about whether it was 6.5 kiloparsecs or 7 kiloparsecs or 8.5 kiloparsecs, but I think we're settled down to something like 8 plus or minus 0.3 kiloparsecs.
One more question from Stefano. Why there is a convergence from initial randomness to planes? This seems common for stars and galaxies as well as for planet orbits.
Right. So the planes are sort of a natural outgrowth of angular momentum. So if you have an initial distribution of matter after the Milky Way and things are sort of coming together, and if there's any kind of net rotation one way or the other, mm-hmm. unless it's completely random, you will end up having those things kind of come together, mm-hmm. and the angular momentum is conserved. And so things tend to fall inward in the direction perpendicular to that angular momentum. So it's really a function of preservation of that angular momentum, unless you can figure out some way to steal that angular momentum away. And one way to steal that angular momentum is by having a galaxy that's happily forming a plane here as a Milky Way, and then all of a sudden you get something like Andromeda. If Andromeda had fallen into the Milky Way early on, it would have taken all the angular momentum that we had been building up and forming a nice coherent pattern and redistributed it, and we would be an elliptical galaxy instead of a spiral galaxy.
Interesting. Well, Dave has one more question. Does the Fe to H ratio, I'm assuming this is the metals ratio,
right,
indicate the age of a star?
That is a good question, and it turns out that it does on broad brush, but not particularly well in the disk of the Milky Way. So let's look at it's this one. Right. Okay. So here we are, and you can sort of see here's the solar metallicity, mm-hmm. and this color scale is age. So you can sort of see, if you just imagine a slice through here at the metallicity of the sun, you can get things that are blue, young, and 10 gigayears old, and we are 5 gigayears. So we would be kind of one of these greenish kind of points. So you can get a wide range in a disk, Milky Way disk galaxy. You can get a wide range of ages at a given metallicity. But one of the reasons you get that is because there is this gradient that the stars form. Let's see, maybe. Yes. So in the inner part of the galaxy, it's very different than the outer part of the galaxy. So I was lumping them all together. And so you can sort of see that if you took a single cut through here at one metallicity, it depends if you're in the inner part of the galaxy or the outer part of the galaxy. So I think that's the answer, is that it works well for elliptical galaxies, for the halo, but it doesn't work very well for something as complex as a disk of the galaxy, because you end up talking about huge swaths that are evolving at different speeds.
All right. Well, I don't see any more questions coming in the Zoom chat. Oh, there it is. So Mark is asking, since you are an astroarchaeologist, do you use any actual comet or meteoroids to as a proof of any of these theories?
So the ratio here, the reason that this is in brackets is because to astronomers, that's kind of a shorthand to compare to the sun. And there is a whole field to make sure that we understand what the chemistry of the sun is. And so, and for about 25 or 30 years, from the 60s through the 80s, there was this huge debate about whether we should use cometary and meteors to determine the chemistry of the original cloud that the sun formed out of, or whether you should take a spectrum of the sun and rely on the modeling of the sun to determine what that cloud that formed our solar system was made out of. And the answer is always more complicated, that for some things, it works better to use the sun and models, and for some things, it works better for the to use those meteors. And it's because chemistry is very complicated, and the meteors have volatile elements, and sometimes those volatile elements form and get turned into other things. So it's not a perfect preservation inside meteors necessarily. Like the volatiles get burned away, so you get a bad feeling for the amount of lithium in meteors compared to the amount of lithium in the sun, or the amount of what's an element that gets burned away easily, not silicon. But if you want to study something that is hard to look at in the sun, like neon, that last row of the periodic table, those things are almost impossible to detect in the sun, but you can detect them in some of the little gas pockets that are locked up in comets and meteors.
Mm-hmm. All right. Well, I think there's one question that just came in. Can you predict this when Sagittarius collided with the Milky Way?
Well, it is continually colliding with the Milky Way. So when did it first fall in? We think it's done about 5 orbits, and each period is 500 million years. So that's about 2.5 billion years ago, I think, is when the first orbit, it came in for the first time. But you can sort of see from this that it's making loop after loop after loop. And some of these early loops are sort of falling apart. They're losing coherence. It's sort of like a contrail on the sky that, you know, as it passes by, it leaves a very clear marker, but after some period of time, you lose that indication. Mm. It's a very hard thing to measure. And so for a number of years, there's the Magellanic Clouds. Mm-hmm. And when I was a young astronomer, the thought was those clouds are orbiting the Milky Way and have gone around on a number of orbits. And now, as we have Gaia, and to actually look in detail as their speed of motion, mm-hmm. the thinking has changed that the Magellanic Clouds are now coming in for the very first time. So that is the next big thing to come crashing into the Milky Way, is the Magellanic Clouds.
That's gonna be, are we gonna be around for that?
Well, you might be around, but I don't think I'm going to be around.
Oh, well, we'll see. I mean, nobody will be around after it happens, probably, right? So,
well, that's the tricky thing, is that when these things come in, if they're small like this, you can sort of see this has made a number of different orbits, and it's kind of a small thing. So it doesn't really, or maybe I should go back to this one. And so if I don't play it, but rather, yeah, so here is an object that comes in and crashes into the Milky Way, or into this galaxy. And you can sort of see it did not disrupt that object, because it's kind of small.
Yep.
But if I show this other one, right at the end, there's a big one that comes through. And you can sort of see it makes one of the spiral arms kind of detach and start moving outward. It doesn't destroy this galaxy, but it does disrupt the orbits.
Yeah.
So it would be unlikely, even the Andromeda crashing into us probably wouldn't destroy the sun, but it might send us off on a little trip.
Yep. That was going to be the next question, because even if like the reason life exists on Earth is like a precise distance from the sun, and like everything just kind of came together, and if we were any closer, we would not be here. If we were a little further, maybe we would not be here. So like that, it will definitely affect in that way then.
I think you've got it exactly right, that we might be living in kind of the Goldilocks region of our Milky Way, and in the Goldilocks region of this particular part of the universe, that we live in what's called the local group. It's not a strong cluster of galaxies where the galaxies are constantly interacting. And that might mean that we're a little bit protected.
Yep. We'll see.
Yeah.
Well, there's one more question about aging the stars, which is on Earth, we use C14 isotopes to date the rocks. Can you study the age of the stars in a similar way to checking for isotope ratios?
Yeah, that's, I had a couple of students early on who worked on that to try to do thorium, uranium to lead age dating. And it was successful. You can do that, but you're sort of piling models upon models upon models. And so if you took all of the biases of your particular models into account, the errors that you ended up with were pretty large. So we were looking for old stars, trying to prove they were old. And so we would end up with things that were 10 or 11 gigayears old with errors of plus or minus 5 gigayears. So they could be as young as the sun, or they could be 1.5 times older than the universe. So that's not entirely satisfactory. And so people have sort of moved away from that age dating and moved towards other methods that don't seem to have quite as many biases and reliance on complicated models.
Well, I guess we are over time, so I'll wrap it up there. Thank you so much for your time, Matthew. This was wonderful. And if you have any more questions, I guess you can send them to me. I can try to pass them on or something like that. So, but anyway, thank you, everyone. Have a good night.
Thank you.
I'm
Good
just going to
skies.
stop streaming really quickly here before, so we don't abruptly drop off.